All right, so our project was creating a tool to identify cell-to-cell interactions that drive differential response to immune checkpoint blockade therapy. So basically, our project goals, immunotherapy releases brakes on the immune system to fight malignant cells and revolutionize cancer treatment. So basically,
sorry, quick note. For those scoring, make sure you score Team 21 for the lesson.
Sorry. So basically, ICV varies vastly across patients and cancer types, and the mechanisms that drive this differential response are often poorly understood, but it's usually involved in the tumor microenvironment, as shown in the figure. The responsive cells and the non-responsive have very different tumor microenvironments. So basically, we want to define these important cell-to-cell interactions to improve treatment. So our aim is to create networks using single-cell RNA-seq data that highlight important cell-to-cell interactions that give differential responses in responders versus non-responders. This has been done in heat maps in mouse cells, but we wanted to create networks that are more able to be visually understood. So our three aims, basically, the first one is to create heat maps of these interactions for us. The second was to use gene enrichment analysis and find enriched pathways to then filter our data set. And then our last one was to create networks. So the first aim was creating interaction profiles for responders and non-responders. And we first started by clustering based on cell type using T-cell plots. There's two B-cell plots, or two B-cell clusters, two myeloid clusters, and 7 T-cell and NK cell type clusters. And then the interaction profiles between the responders and non-responders are drastically different, as you can see. So in responders, G4, G7, G9, and G11 are more expressed in responders, which makes sense because G4 cells are dendritic cells, and these play an important role in antigen presentation for formation of reactive T cells and T cells. And then G9 and G11 are both exhausted cell types, which makes sense why they would be less dominant in non-responders, as they are exhausted cells and do not interact as much.
Just to clarify, we're using a melanoma data set that is able for responders and non-responders to anti-P1 and anti-CTLA-4 treatments, and it's sorted only for immune cells, and that's why we're only showing immune cells. So next, we have this massive interaction maps of like all possible receptor-ligand interactions between all the stimulation cells. So we wanted to narrow this down and make it more biologically relevant. So we proceeded to do differential gene expression between responders and non-responders for every cell type to find pathways that might explain the differences we were observing in our heat maps. So here I'm showing the cells. Once we have performed differential gene expression, we came up with these significantly differentially expressed genes for each cell cluster. And despite the value of differential gene expression, it remains difficult to interpret genes in isolation. So we decided to take these gene sets that are significantly differentially expressed and perform pathway analysis on these significantly expressed gene sets and come up with this enriched pathway results that would enable, we hypothesize, for filter interaction, of course, and have a better understanding of what were meaningful biological receptor leads to focus our analysis on. So we were confident that our pathway enrichment analysis worked because most of the enriched pathways are related and coherent with their cell type of origins. For instance, B cells show enrichment for BCR signaling, T cells for like interfering and BCR signaling, and myeloid cells for anti-cross presentation and neutrophil granulation. But what was even more encouraging to see was that in yellow we showed a lot of the pathways that have been previously associated with melanoma progression, and also immunoglobulin resistance, such as interferon gamma signaling, PD-1 signaling, or CD28 co-stimulation.
And then this is basically our dimensionality reduction strategy for going from our large data set down to these networks of cell-to-cell interactions. So basically, we start with our original transcripts per million matrix up at the top, and we kind of go down two different paths. The first path was A1, where we created the first interaction scores. So we split by cell type. So we had 11 different clusters based on our cluster against the T-SNE. And then we split by response. So we had the 22 of the responders and non-responders. And then we calculated the average gene expression within all those sets. So we had 22 with the average expression of all the gene types. And then we create interaction score matrices for all pairized type combinations, as mentioned before. So G1, G2, G1, G3, and then for both receptor ligand pairs. And then on the right-hand side, we have the AIM2, which was the gene pathway enrichment analysis. So basically, we split by cell type, so we again have 11 of those with the responder and non-responder, and then we create a differential gene expression where we have the DEGs for G1 through G11, and then we create our enrichment analysis where we get our list of enriched receptor ligand pairs. And then basically we use these lists to for interaction score filtration, where we have a binary classification. So if the receptor ligand pair was enriched in both cell types, we would keep that pair. Otherwise, we would just discard it. And then we create holistic interaction matrices with these updated receptor ligand pairs, creating new heat maps for responders and non-responders with average interaction score matrices, which we use as our weights for our edges in the networks.
So our final result is shown here, and essentially we're showing the networks for cells. Sorry about the confusion is not great. I'll show my best for like the labeling of the nodes, but the nodes are cell clusters, and they're scaled by number of cells in that cluster, and then edges are weighted by interaction, average interaction scores. And what was really encouraging to see was that a lot of the canonical changes that we would expect with the development of resistance to immunotherapies are consistent with our networks. But what was even more interesting for us was to see that actually the most unexpected, which was like the G2 cell cluster, which is our two plasma cells. We were expecting something important to be going on with T cells, seemed to be like key in like orchestrating the immune response. And we actually found this paper published only a couple months ago that said that B cells differentiate in the plasmablast-like state that actually orchestrates associated melanoma-associated inflammation and response to like immunotherapy, and they seem to be like key. And indeed, we see that this G2 cluster has important interactions with like several like G7, G6, G9 exhausted and regulatory T cells we would expect, and also like the G2 responders and non-responders, we see an increase in this plasmablast-like state and a decrease in the B cell-like state. So it suggests a transition from this B cell to this plasmablast-like consistent state. And what wasn't touched on in the paper that we found in the results was actually that this really strong change in the interaction between the plasmablast-like state and the myeloid cells that increased significantly in non-responders. And myeloid cells are going to be suppressor cells in the tumor microenvironment in non-responders. So we hypothesized that this specific interaction is could potentially open a new research avenue for the understanding of the development of resistant in melanoma. So we thought that was a really cool finding from our project. So in summary, we put together a pipeline that enables to generate what we think are more biologically relevant and interpretable networks using differential gene expression and enrichment analysis using chemotherapy data. And we have also applied this to melanoma, and we've identified a new research avenue to understand resistance to immunotherapy in melanoma. And yeah, future work could be expanding the gene sets for enrichment analysis, quantification, normalization, and data filtering strategies for over and under represented cell types.
Great. So I'm curious, how do you get at the cell-cell interaction from the single-cell data? Are you using correlation there, or what do you think?
So basically, it's a transcripts per million matrix. So we just did for interaction scores, transcripts per million matrix. Yeah. So basically, we had a list from SciNet of like these immune receptor ligand pairs, and we basically filtered for those like genes expressed, and then if there was a pair between the two.
It's an average.
So SciNet is looking at known protein interaction networks and projecting that at a single cell level. Is that what you're doing?
What we're doing is that using Synapse to filter like receptor and ligand genes, and then if they're both like if you have expression of the receptor and ligand, you get average expression of the
Was that in your presentation?
I think we tried altering that.
Okay.
That was how we arrived at this.
Yeah, but I couldn't see it.
Yeah, we didn't.
Okay.
It's a
So now that you have the cell-cell interaction, that's sort of the main driver. How do you get at the genes that are driving this? These are the ligands and receptors.
So we have these receptor ligand interactions first, and then what we try to do to reduce the dimensionality essentially is to filter for genes that appear to. So we basically do differential gene expression between responders and non-responders for say the G1 cluster, and we find genes.
But these are clusters of no, these are just cell types. You want
Yeah. So what we do is differential gene expression between responders and non-responders for each cluster in the protein. So those are meant to be like important genes.
Sure.
We then do enrichment analysis to kind of interpret those important genes, and we extract from the enrichment analysis all the genes that are enriched in general in that pathway.
Yeah.
And then from those genes, we get the receptors and the ligands that are in those genes. And then we say, if these are like differentially expressed and enriched, we assume they're going to be important genes.
Okay. Other questions? Okay, great. Thank you. Next. Who has to go?
We are Team 14.
Yeah, so we're going to do full screen from scratch. So
I think they're next in.
Yeah, we're
okay. Anyone else want to leave or no? Okay, great. So let's go back to the big one. Here it is. Okay, perfect. Great.